Hello and welcome. I'm Saeed Fadaei from the University of Surrey, and today I'm presenting the work that we spent last year and a half trying to answer. When the sun gets angry, does your satellite internet get worse? And more importantly, can we prove it end to end? Most people think of solar storms as the thing that gives you a beautiful aurora photograph, but the historical record tells a different story. For example, in 1859, the Carrington events sent current through telegraph wires so strong that operators reported sparks and fires. Or in 1989, a geomagnetic storm took down the Quebec power grid that resulted into 6 million people went without electricity for 9 hours. Or in 2003, the Halloween storm disrupted polar aviation routes and took GPS offline. And luckily for us, there wasn't no smartphone back then in old days. And in 2022, much closer to home, for those of us in the networking community, a moderate geomagnetic storm contributed to the loss of 38 out of 49 Starlink newly launched satellite because of increased atmospheric drag that prevented them from raising in orbit. But here is what none of those historical events answered. What actually happens to real satellite internet performance when an extreme or severe storm hits? I mean, not the hardware, not the power grid, the network that millions of people are using. And that is the question that this paper answers. And to answer that, what is our methodology? First, a control network view through LEOScope. LEOScope is our own global testbed of known Starlink nodes, running time triggered measurements with built in telemetry to give us precision in this measurement campaign. Second, a global geographic view through MLab's NDT7 speed test dataset that includes thousands of cities, millions of tests, and letting us compare storm versus quiet days across different latitudes to give us a scale in the measurement campaign. Third, a user experience view through MLab through Cloudflare AIM dataset, which goes beyond throughput and latency to give us scores for voice over IP quality, gaming, and streaming. And this is going to be our user impact in the measurement campaign. And fourth, an orbital operations view through TLE maneuver detection to let us see how Starlink actually moved this fleet in response of the storms to give the measurement campaign the operator response. Um, Now we need to briefly explain the physical mechanism of this solar geomagnetic storm. It's important for interpreting what we are going to discuss in this paper. When a solar storm hits Earth, two things happen that matter for satellite networks. First, the thermosphere. The upper atmosphere where LEO satellites operate heats up and expands. This increases atmospheric drag on satellite and forces operators to compensate with maneuvers. Second, the plasma irregularities in the ionosphere can disrupt the radio links between the satellite and the ground terminal. Our study focuses on two G5 geomagnetic storms as extreme storms, one in May and the other one in October 2024. The May storm, now called the Gunnan storm, was the most severe this century, which was in a Carrington level class. To give you a primer about the space weather itself, we need to first introduce KP index or KP, the K planetary index. The KP index measures global geomagnetic activity in a scale from 0 to 9, quantifying the disturbance in the Earth's magnetic field. NOAA classifies geomagnetic storms using this K planetary index from G1 as the mildest to G5 as the most extreme one. G5 corresponds to a KP of equal of 9 and occurs only about 4 times per solar cycle, roughly every 11 years. G4 is severe, occurring about 60 days per cycle, and G3 is a strong and equal to KP index equal to 7. It's frequent about 130 days per cycle. Our paper covers all 15 G3, G4, and G5 storms that occurred across the 1.5 year time window from May 2024 till October 2025. And this is going to be the most comprehensive study so far in this kind. Right now, we know the physical um, nature of the solar storms, and we know how to measure it. But to have a recap about and give you a brief on the map, give you a brief overview on the map, how does the measurement look like? LEOScope was supposed to be for the time and the location precision, and the MLab as a, of course, as a blue rectangle, and the MLab NTT7 was supposed to be for geographic diversity and scale as the yellow triangles, and the Cloudflare speed tests for end user experience as red circles. But we have two dashed lines and red areas, considering and showing KP index equal to 8 and 9 as the roughly latitude equal to 40 degrees, showing the regions that are aurora are visible. Now that we know what's our expectations from LEOScope, let's dig through how we have our architecture of running the measurement campaign. When NOAA forecasts an elevated KP index, our orchestrator arms a trigger on all LEOScope nodes. The moment that KP exceeds the value of 5, continuous iPerfs and high cadence session begin, and I mean one iPerf test per minute. Two iPerf servers we control in London and Chicago. Simultaneously, LEOScope reads from Starlink's own gRPC telemetry API, giving us dish connectivity drops, obstruction levels, and latency to the point of presence. This means we are not comparing randomly collected speed tests. We are comparing the same nodes, the same servers, at the same of the day or night during storm versus non-storm quiet conditions. But what have been the results of running measurements through LEOScope? Across five most instrumented nodes as London, Munich, Abuja, Osnabrück, and Victoria, the bars show the percentage change going from quiet days to extreme storm conditions across three metrics: throughput in purple, RTT in green, and congestion window size in pink. The pattern is consistent across all four high latitude nodes. Throughput drops, RTT increases, and congestion window shrinks, which reflects how aggressively TCP is able to send and shrink the bandwidth. Abuja in Nigeria, on the other hand, sitting well below 40 degrees of latitude, shows almost no effect, and this is our within dataset control, and we're going to verify it with other datasets later on. To continue with another use case, another case study, another case study in London, we looked at the drop rate directly, and the top panel shows a 6-hour quiet period, meaning the KP index equal to 2.6 with a 4.17% drop rate. But on the bottom panel shows a 6-hour time window during the October extreme storm, meaning the KP index was more than 8 and equal to 8.47 with a drop rate of 9%. And the result was fascinating. This was more than a doubling of the packet drop rate. And interestingly, it's not just a spike, it is sustained and elevated across the entire time window. And this is a systematic effect. Let's continue with another case study. Now, let's look at Oslo node, the northernmost point in LEOScope, to give us a second measurement lens through continuous Ookla speed test during October 2024. The result here that we've seen from the speed tests were stark. Median download throughput drops from approximately 170 megabits per second during quiet days to around 120 megabits per second during the extreme storm, a roughly 30% reduction. Upload, on the other hand, shows the same pattern, falling from 15 to 11 megabits per second as well. These are user-facing speeds on a consumer Starlink dish in one of the most geomagnetically exposed locations on Earth with beautiful aurora sceneries. As two other metrics in the Oslo dataset and case study, On the left, hourly median RTT, the dark storm curve, sits consistently above the red non-storm baseline across the entire storm window, with the gap widening as KP peaks on October 10th. On the right, also, dish connection drops, measured as failed link checks per hour, increased from a median of about 0.2% under normal conditions to nearly 1% during peak storm hours. And this is a fourfold increase in satellite link instability measured directly from Starlink's own telemetry. And we know we know that the LEOScope results are precise, but they cover only a handful of locations. The natural question is this global? To answer that, we turn to MLab's NDT7 dataset and I'm talking about over 1.2 million satellite speed test records across more than 2,500 cities in 240 countries. This is inherently post hoc. We can't control when users run a speed test. So we use a standard space weather methodology for baseline selection, ranking days within each month by KP index and identifying the five quietest days as our control. And we are stratified by latitude. I mean, regions above 40 degrees north or south are affected latitudes, and everything else is going to be considered as control latitudes. This boundary accounts for the fact that Starlink satellites have a roughly 1,000-kilometer ground footprint, which translates to about 9 degrees of latitude span. So even cities slightly below the aurora boundary may be served by infrastructure in it. Now that we have a definition for, or the reason why we are using MLab dataset, let's validate the throughput pattern. This box plot of the 95th percentile download throughput across representative cities in both control and affected latitudes is showing that on the left side, the control cities, the control latitude, sorry, as Buenos Aires, Jakarta, Lisbon, on the storm days and quiet days are essentially indistinguishable. But when we look at the affected cities on the right, Seattle, London, Berlin, and Calgary, in every city, the storm distribution shifts downward, and the median of the throughput drops, and even the upper tail compresses. The effect is consistent across continents. And for going forward, as another example with MLab, uh, we should investigate that the throughput shift reason, but what and find out what's driving it. This slide is going to tell the story with the example of America continent. We looked at the packet loss and TCP retransmission rates across the Americas, comparing countries in the affected zone, I mean the US and Canada, with controlled countries examples of Brazil and Argentina. The onset of the October 2024 storm is visible as a sharp spike in both loss and retransmission in the US and Canada. But for Brazil and Argentina, on the other hand, show nothing comparable. The storm signature is geographically precise. This is also significant that the dominant pathway is not RTT inflation. It is increased loss, which then causes TCP to back off and reduce throughput. The ionosphere is essentially injecting packet loss into the link. And to continue with our case studies with MLab and DT7, uh, we can go further using reverse DNS lookups on MLab client IPs to identify which Starlink point of presence each speed test was served from. And we have considered 5 examples: London, Frankfurt, Chicago, San Jose, and Calgary POPs, and compare a storm versus quiet performance at the pop level. And the takeaway is the loss rate is the metric that increases most consistently and most strongly across every pop location. And the RTT changes are also real, but smaller compared to the loss rate. And the throughput decreases are partially buffered by the TCP's retransmission mechanisms. This pop level granularity lets us confirm that the effect is infrastructure wide, not a local artifact. And one interesting finding that we did not originally plan for was in every country within the affected latitudes, from US down to New Zealand, The volume and or the number of speed tests on MLab increases dramatically during storm days compared to quiet days. And by increase, I mean even in US, we've seen that 149 percentage increase in the number of speed tests compared to the non-storm or quiet periods. But on the other hand, in controlled latitudes, Indonesia, Argentina, Nigeria, Mozambique, or Portugal, the pattern is flat or slightly down. People uh, in affected countries were can this can be a takeaway, right? The people in affected countries were running a speed test because they noticed something was wrong, or they find it interesting because of the solar storms. And this is going to be indirect evidence of user perceived degradation at massive scale, and it's consistent with the quantitative metrics that we have found so far. We have gone through LEOScope, we have gone through the NDT7 as the post hoc global validation, but is the impact real or the same in other constellations as well? When we compare LEO versus MEO and GEO, and we filter MLab speed test by the type of the satellite operator, and I mean the ASN classification from prior related work, we see that in the storm day versus quiet day performance within the affected latitudes, LEO RTT increases or throughput are experiencing the degradation from 8 to 8%. But the packet loss, we saw that interestingly, it's even more than doubling up in Leo. But when it comes to Mio, the differences are smaller and the range of degradation is the maximum 5% compared to the baseline of the non-storm periods. But when we coming to Geo, the differences are absolutely negligible. We, when we compare to the baseline, everything is flat. And the storm impact on loss is dramatically concentrated in Leo, as we can see. And Mio is moderately affected, but Geo is largely resilient. How can we justify it? Because the physical mechanisms. When we are talking about the atmospheric drag and ionospheric plasma irregularities, Leo are far more severe and flying in more severe altitudes. Geo, on the other hand, operate at 36,000 kilometers, and it's going to be well above the affected layers. But when it comes to Leo, as said, it is far more severe. It flies in 550 kilometers directly through the storm. And to be clear about the context, despite the degradation that these constellations are experiencing or not, Leo still offers far better baseline performance, RTT in the range of 91 milliseconds and 51 megabits per second throughput, versus the Geo that provides 900 milliseconds and 7 megabits for Geo. The storm doesn't change which orbit class we're going to prefer. It just reveals its vulnerability to solar geomagnetic storms. If we continue to see what is the impact and how does it translate to actual user experience degradation, we know that we are going to use Cloudflare AIM's application quality scores for voice over IP, gaming, and streaming, each graded on a 5 level scale from bad to great, from 1 to 5. And finding here is nuanced because storms do not collapse the service. The majority of sessions are still a score good or great, but what we see consistently across all three application types is a 1 level downgrade. Great scores shift to good, and average scores slip to poor. The combined proportion, on the other hand, and I mean good and above, stays roughly stable, but the composition worsens. In practical terms, when I am doing or you are doing a video call, probably it's going to stay connected, but it becomes noticeably less comfortable, and so on and so forth with the gaming and the streaming use cases. It's gonna feel laggier, but the connection is going to persist. Let's now go through the transport protocol. One of the key differences, one of the key differences between the NDT7 and the Cloudflare AIM speed test is the BBR and the cubic congestion control mechanism that these two speed tests are using. During quiet days, BBR algorithm already outperforms cubic, mean lower loss, higher throughput, lower RTT, and this is consistent with prior work showing BBR's advantage on normal conditions, obviously. But during this storm, the gap widens. Cubic's quiet day packet loss rate is comparable to BBR's storm packet loss rate, or Cubic's quiet day throughput is worse than BBR's storm throughput. The implication here is clear. If you are operating over LEO satellite links, and especially if you are operating in high latitude regions, your choice of congestion control algorithm is not an implementation detail. It is a resilience decision. BBR is substantially better suited to the dynamic high loss conditions that storms create. We have gone through the measurements, we've seen the impact of the solar storm, but does it mean that the providers stay put and do not do an attempt on fixing their fleet? The network story does not exist in isolation. There is an orbital story running in parallel. To see it, we collected over a million two-line element records as TLE from a spacetrack.org for roughly 6,700 Starlink satellites across May and October 2024. These TLEs are the standard format for encoding a satellite's orbital parameters, updated approximately every 3 hours by operators. Our detection method is straightforward. For each consecutive pair of TLEs, we propagate the earlier one forward to the epoch of the later one and check whether the satellite's actual altitude differs from the predicted altitude by more than 100 meters over a 3 hour window. If it does, a maneuver occurred. This is a well established technique for inferring thruster firings from the public tracking data. What we seen what we saw as outcome is interesting. The result shows that during the May 2024 storm, nearly 50% of Starlink's entire active fleet maneuvered on the peak storm day. And the same pattern goes on with the October. The October shows that a storm uh, pattern is similar. And we see the same spike, around 40%, compared to a baseline of about 12% on quiet days. Starlink was not passively observing the storm, and we know that. They were actively moving thousands of satellites, almost certainly to contract and increase atmospheric drag and prevent the kind of orbital decay that destroyed 38 satellites in February 2022. But here's the network implication, right? Satellite maneuvers change inter-satellite link geometrics, possibly. And they can also disrupt handover schedules and introduce transient connectivity gaps. These maneuvers that protect the hardware are themselves contribute to factor or network degradation we measure. For comparison, uh, and consider the geo providers, these operators, I mean geo operators, show no significant change in the same period and no maneuver detected during either May or October storm. And as expected, at 36,000 kilometers, they simply do not experience the same drag forces as the LEO constellations. Let's wrap it up and close the key claims. Space weather is now an internet measurement problem. The sun's activity during the current solar cycle directly and measurably degrades the performance of the satellite internet that millions of people depend on, at mid to high latitudes, of course, across every measurement vantage point we used. Storms degrade LEO measurements at every layer we examined, on controlled hyper throughput and drop rates, MLab speedtests, and Cloudflare AIM quality stores, and Starlink's own telemetry. The effect generalize globally and concentrate in affected latitudes by above 40 degrees. But control latitudes see little or no degradation, providing a clean within dataset validation. And, and finally, the choice of congestion control could matter. BBR is showing more resilience to high loss and dynamic conditions that a storm creates on LEO links. And as solar cycle 25 approaches its peak or crossing it, and as internet dependency grows, understanding and designing for a space weather is no longer optional, and we should know that. And I want to thank you for the opportunity for presenting our paper.